Do you feel the vibes?
Hey guys, so we are going to talk about 6.4 today, partial fractions. Yay! I'm actually kind of sad I'm not there because I love teaching this lesson, but it's okay. All right, so take a look at what we're going to do here. So you know how when, we have like a quadratic equation like this one, we can factor it, right? And by doing that, essentially we come up with two simpler expressions that multiply to get that more complex expression. Well, guess what? You can do the same thing with a rational expression of, something that has a numerator and a denominator. You can actually come up with two smaller fractions which add to the more complex fraction, right? So these simpler rational functions that we're going to come up with have constants in their numerators. And the process by which we do this, right? We say we decompose a fraction into two partial fractions. And the whole thing is called partial fraction decomposition. And if that isn't a mouthful, I don't know what is. So take a look at this, right? You've got this fraction here. How did that come about? Well, basically, it's the addition of these two that produced that. So what we're going to do is we're going to be given this more complex one, and then we're going to decompose it into the two simpler fractions, the partial fractions from which they came. Okay, so let's actually do that one, right? So the way I've done this is there are three cases that we're going to look at. The first case is when you have a denominator with linear factors, okay? And we'll see what that means right now. So in this case, it says to find the partial fraction decomposition of this expression. So here's what you do. You take the fraction that you're given, okay? And, actually, you know what? I want to factor the denominator here. So this is going to be x minus 5, x plus 4, right? So this is where this first case is, right? So look at this. Case 1, it's a denominator with linear factors. And if you can see here, this denominator does have two linear factors. So we factored this. Now, this is equal to. So look at this denominator that we factored. However many terms it has, that's how many new fractions we're going to get. In this case, it's 2. So we're going to get two new fractions. One gets the x minus 5, and the other one gets the x plus 4. Okay, the numerators of these are going to be constants. So how do we know that? In general, the numerator of these partial fractions is going to have one less degree than the denominator. So in this case, if the denominator is x to the power of 1, the numerator is going to be a constant, right? As placeholders, we put capital A and capital B. If I had three fractions, it would be A, B, C, and then D, and then E, and so on. Okay. Now, at this stage, we're going to multiply through by the LCD. The LCD of these, right, is x minus 5, x plus 4. So let's do that. Okay, don't discriminate, right? Everybody gets the same treatment. And then when I, cancel things out, right, what do I get? Here I get x plus 13 is equal to A, x plus 4 plus B, x minus 5. At this stage, we are now going to solve for a and b and all the other constants, really. Okay, how do we do this? One way to do this is the following. We're going to plug in values into this equation for x. Okay, but how are we going to choose those values? Well, we're going to do it in a very clever way. We are going to choose values that make either this parenthesis or this parenthesis equal to 0. Okay, so what makes this x minus 5 equal to 0? When x equals 5. So we plug 5 into all the x's. 5 plus 13 is equal to a, 5 plus 4 plus b, 5 minus 5. So 18 is equal to 9a plus 0, right? Oh my god, look at that. A is equal to 2. Wow. Okay, next. So next, let's look at what makes this parenthesis 0. Well, that's if x equals negative 4. So negative 4 plus 13 equals a, negative 4 plus 4 plus b, negative 4 minus 5. So here I get 9 is equal to 0 minus 9b. So b is equal to negative 1. Okay, there we have it. So now our fraction is equal to a, which is 2 over x minus 5, plus b. But what's b? It's minus 1, right? So I put the minus here, 1 over x plus 4, and there you have it. We're done. And if you don't believe me, if you just add those two, right, common denominator, blah, 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 you know what? You would get that equation you would get that expression at the left. Isn't that super cool, right? So just be careful, right, that you don't mix up like a and b, right? Initially, a went with the x minus 5. So whatever you got for a, which is the 2, that goes with the x minus 5. Okay? Now, what happens if you had, switched them? Like what happens if you had done a over x plus 4, b over x minus 5? Really nothing. Then whatever you get for the x minus 5, you give it to the x minus 5. Okay, let's do another one. Now, what if you have an improper fraction? In this case here, we didn't have an improper fraction. Why? Because the degree in the numerator was less than the degree in the denominator. An improper fraction is when the degree in the numerator is equal to or greater than the denominator. In this case, we have to do long division, yay, to write the fraction in this form, and then you have to decompose the fraction. Okay, take a look at this one. I purposely pick one that's like this. So look, we have x squared on top, x squared on the bottom. This is an improper fraction. So first, you have to divide. So as soon as you see your fraction, first decide, is it improper or not? Do I divide or not? And then go from there. Okay, so why don't we divide this because we miss doing that. I can never get enough of this, let me tell you. I mean, it's actually like, 11:30 right now at night that I'm doing this. And, still so much fun to do long division. Okay, let's do this. So negative 2x squared over x squared, right? I get negative 2. And then you multiply plus 2x. Remember to switch the sign, right? Draw the line and combine. So what do I get? 7x minus 4. Once this in the bottom has a lower degree than your divisor, you're done. So now that is my remainder. The 7x minus 4 is my remainder. So this ends up as an equivalent expression of negative 2 plus 7x minus 4 over x squared minus x. Fabulous. Now, I need to decompose this. Okay, so let's do that. 7x minus 4 over, why don't we factor this, equal to. Okay, how many fractions do we need? 1, 2. Always plus. So the first one gets the x, the next one gets the x minus 1. Let's multiply by the LCD. Oh, no. What do I write on top? A and B. Let's multiply by the LCD. So what do I get? 7x minus 4. Whoops, not that one. Is equal to A, x minus 1, because the x's cancel, plus B, x. Cool. Okay, what makes the first one 0? 1. So 7 minus 4 is equal to A times 0 plus B times 1 equals B. Okay. What makes this one 0? Oh, 0. Okay, so 7 times 0 minus 4 is equal to A times negative 1 plus B times 0. Negative A equals 4, so A is equal to 4. Aren't we having fun? Okay, now let's write this. We started out with this. This is equal to. First thing you got to do is include this negative 2 plus A 4 over x plus B 3 over x minus 1. And that is your partial fraction decomposition. Okay, so now at least one of you are wondering, Mrs. Malikin, do we always have to write this, in the beginning? The answer is no. I mean, the proper way is, okay, so now this is equivalent to that, but really this is good enough. Okay. That was case 1. What was case 1? If you had a denominator with linear factors. So, case 2. What if you have a denominator with repeated linear factors? What then? Well, if the denominator of a rational expression has a repeated linear factor n times, then the partial fraction has to have a repeated fraction for each of those. Okay, what do I mean by that? Take a look at this. This is 5x minus 1 over this mess. So what do we have here? We have x cubed, which is really x times x times x. And then we have x minus 1, x minus 1. So do you see in the red, I have a linear x that's repeated 3 times? That means I need to have 3 fractions devoted to those x's. And the way it looks is, I start with x to the 1, and then I increase the exponent by 1 until I reach this maximum exponent of 3. So I have x to the 1, x to the 2, x to the 3. Then I have a repeated x minus 1 twice. So I need 2 fractions dedicated to x minus 1, starting with x minus 1 to the 1, x minus 1 to the 2, done. Now, remember, technically, each of these are still linear terms, right? They are just raised to exponents. So x is linear squared, x is linear cubed. Here, the last one, x minus 1, is linear, but then it's squared. Each of these gets a constant, a, b, c, d, e. Okay, and then we do the same thing. So why don't we do this one, right? Then bear with me, and then you'll see the difference for when the denominator is not linear. Okay, you'll see the difference. So here, let's factor this. First, I can take out an x, right? So what I have here is, oh, by the way, is this an improper fraction? No, right? Because the numerator on the top is low, has a lower degree. So I don't need to divide. So 3x squared minus 5x plus 4 over x. And when I factor that one, I actually get x minus 2 squared. So I'm going to get 1 for the x, 1 for the x minus 2, and then 1 x minus 2 squared. So that x minus 2 is the one that's repeated, so that gets multiple ones. On top, I got A, I got B, C. Yay, okay. So we're going to multiply this by x minus 2 squared, and same with this, okay? Love it. So 3x squared minus 5x plus 4. Okay, so this one's going to be A. Remember, we're going to distribute this, right? X minus 2 squared plus BX, x minus 2, plus C, x. Okay, same deal. First, let's make this x minus 2 0. So I'm going to take x equals 2. So 3 times 4 minus 10 plus 4, that's a 6, equal to A times 0 plus B times 2 times 0 plus C times 2. 6 equals 2C, C equals 3. Great. Now, okay, let's make like the x 0. So 4 equals to A negative 2 squared plus B times 0 plus C times 0. 4 equals 4A, A equals 1. Okay, so now I'm done. Like I'm out of numbers that make these terms 0. Okay, does that mean I'm done? No. Technically, I really could have plugged in any number I wanted. I could have plugged in x equals 152. I just chose the ones that make these 0 because it just makes everything so simple. So this time around, why don't we just, plug in a random number? Okay, somebody give me a random number. Oh, did somebody say 1? Yep, x equals 1. Let's do it. So 3 minus 5 plus 4, 2 is equal to A times negative 1 squared plus B times 1 times negative 1 plus C times 1. So I get 2 is equal to negative A minus B plus C. But wait, I know what A and C are. So 2 is equal to negative 1 minus B plus 3. So B is 2. Okay. What I have now is A 1 over x plus B 2 over x minus 2 plus C 3 x minus 2 squared. And no, I did not choose those because it was 1, 2, 3. But there you have it. Okay? Yay! Moving right along. Okay. Lastly, this is so sad. This is the last page of this chapter. Case 3. What if we have a denominator with prime quadratic factors? So now what if the denominator is not linear anymore? If the denominator of the original expression contains a prime quadratic factor, then the partial fraction decomposition has to have a fraction with a linear numerator. like bx plus c. Okay, what do we mean by that? Let's talk about what linear form is. Our favorite linear equation is what? Mx plus b. Okay, what is this really? M, constant. B, constant. Why does it have to be M and B? Why can't it be AX plus B? Why can't it be BX plus C, right? It could be any of these. It could be CX plus D, okay? So take a look at this right here. I have an X, and then I have an X squared minus 1. Now, I'm sorry, X squared plus 1. Now do you see the difference here? The X squared plus 1 cannot be factored anymore. So this is different from the X minus 1 squared. That was X minus 1 linear. It was just quantity squared. Now this one, X squared plus 1, is like perpetually a quadratic expression, right? So in that case, when I separate them, I have one denominator of x, that gets an a. Then I have another denominator of x squared. That numerator has to have one less degree. So if this is a quadratic, the numerator has to be linear. And so when I make it linear, it's like mx plus b. I used a, then I go to the next one, bx plus c. Okay? Fabulous. Let's do this one. It's factored. Can't factor it anymore. So x cubed minus x over x squared minus 3 squared is, this is a repeated one. It's repeated twice, so it needs 2. X squared minus 3. X squared minus 3 squared. Numerator ax plus b, then cx plus d, right? Fabulous. Okay, so just take the stuff inside, right? So this isn't like x to the 4. Okay. What's the common denominator? X squared minus 3 squared. So here I get x squared minus x, or x cubed minus x, is equal to ax plus b, x squared minus 3 squared, plus cx plus d. Okay. You know what? Okay, so we're going to solve this one in a different way. Okay. X cubed minus x is equal to, why don't we, oh, I made a mistake. Miss Malikian. This one should not have been a square, right? Because if you multiply this by this, you just have x squared minus 3. Okay, sorry about that. So what we're going to do is we're going to FOIL that. Let's see what we get. First terms, ax cubed. Outer terms, minus 3ax. Inner terms, bx squared. Last terms, negative 3b. Plus the cx plus the d. Okay, now we're going to group by powers of x. Okay, x cubed minus x is equal to, okay, so let's look. Okay, I have an x cubed, it's alone. Okay, do I have any x squares? Yeah, bx squared, right? Let's just sort it. Okay, do I have any x to the ones? Yeah, this one and this one. So minus 3ax plus cx. And then do I have any constants? Yes, negative 3b plus d. Now, take a look at what I'm going to do. X cubed minus x is equal to, okay, so this x cubed is alone. The x squared is alone. Here, I can factor out an x, right? So this will be plus negative 3a plus c times x. I'm going to factor it like to the right. And then these are all constants. So I can do plus negative 3b plus d, right? I'm just grouping them by the powers of x. Now, here's what we're going to do. We are going to compare the coefficients of like terms. Okay, what do I mean? Here's what I mean. Here, this is my x cubed term. What is the coefficient of x cubed in that term? A. On this side of the equation, where is the x cubed term? Right there. What is the coefficient of that term? 1. So if the left and the right are the same, that means for each term, the coefficients have to be equal to each other. So if this x cubed has a coefficient of a, and the other x cubed has a coefficient of 1, then a is equal to 1. Now let's move on to the x squared. Here, I got that in green. I want to make it green. Okay, the coefficient of x squared is b. Here, is there a coefficient of x squared? Is there even an x squared? No. That means if there is no x squared, it's equal to 0x squared. So b is equal to 0, right? So let's say that again. On this side, the coefficient of x squared is b. On this side, it's 0. Okay, now let's do c. This is the coefficient of the x, right? That's the coefficient of the x. So what is that? Negative 3a plus c. On this side, what's the coefficient of the x? Negative 1. So this is equal to negative 1. Okay, let's see if we can solve that. Negative 3, oh, a is 1, plus c equals negative 1. So c is 2. Yep. And lastly, this is a constant, negative 3b plus d. What's the constant on the left-hand side? Nothing, so it's 0. And so this is negative 3 times 0 plus d equals 0, d equals 0. Okay, you're probably wondering, why on earth is this lesson in the matrices chapter? Well, because like here you have 4 unknowns. You can technically in this method create 4 equations and solve them as a matrix, but this is more fun. Okay, so now let's see what we got here. So our original equation was x cubed minus x over x squared minus 3 squared. This is equal to, the first denominator was x squared minus 3, and I had ax plus b, 1x plus 0, right? So that's just x. Plus cx plus d. What's c? 2. 2x. What's d? 0. X squared minus 3 squared. There you have it. Okay? All right. So your homework is from the book. And I've actually posted solutions to all the problems on my JAG. So you can have that with you, okay, when you're doing the homework. All right. Have a good day, everyone, and I will see you soon.
Press start.